and performant. DX12 enables the imminent post-launch implementation of ray tracing. Imminent post-launch implementation of ray tracing.
Imminent post-launch implementation of ray tracing.
Oof, I might have been a bit naive back in September 2018 when I said ray tracing support for Shadow of the Tomb Raider was going to be imminently releasing. So here we are about 6 months and some later basically, and there's been an update to Shadow of the Tomb Raider adding in ray-traced shadows and deep learning super sampling into the game. Originally, I started out this video shortly after the patch was released, and it was going to be a very standard video just talking about that performance, the looks, etc. of that implementation, but the chance offered itself and I decided to take a different approach here. I had the opportunity to set up some interview questions with the very people responsible for this implementation of ray tracing in the game, both from Nvidia and Nixxes, that awesome porting company responsible for Tomb Raider's PC version here, and I thought it would be a great idea to make a video out of this interview. It's a bit different than my usual approach here to these things, but a unique opportunity that I really couldn't pass on. The conversation was done non-locally, so there are some quality issues regarding the audio at times, and one of the participants, Michael Rosa's mic, ended up not working at all. So I had to read off his responses from a textual chat. So it is a little rough at times, but it is chock full of information and I hope you enjoy it. But enough from me, let's get over to that interview with the introductions from the various participants who worked on ray tracing in Shadow of the Tomb Raider.
Yeah, sure. I'm a developer technology engineer and work with NVIDIA, and I've been working together with John and Nixxes. I hope Michiel might join us later on, an engineer from Nixxes as well, to make it to have DXR shadows in Shadow of the Tomb Raider.
I'm here. I'm mostly here just to listen in, and I'm a senior graphics programmer and have been deeply involved in the ray tracing stuff, and I'm also a fan of Digital Foundry stuff, so I thought this would be a cool opportunity to get people to learn more about what Holger and John and everyone has done for Shadow of the Tomb Raider.
Hi, I'm the manager of tech engineering for Western Europe. The main focus of my role is integrating cool new tech into great games like Tomb Raider.
Jurgen Katzmann, I'm studio head and technical director at Nixxes. So I'm hoping to tell you guys a bit more, any questions you have about sort of the tech we built for Shadow of the Tomb Raider, and one of our engineers, he was our main engineer on this project, is currently on vacation, but he was going to try to call in, so we'll see.
I'm here, yeah.
Hey, I'm Michiel. Hope you're having a good vacation. Thank you for joining.
Hi. Yeah, great. Thank you. Yeah. Hi, I'm Michiel. I'm a graphics engineer. So, Michiel, we just lost your line there.
Since Michael Rosa is having trouble right now with his mic, I'm just going to actually read off all the things he types here in our chat. So the first question I would actually start off with on the Nixxes side of things would be, when we came to Shadow of the Tomb Raider and its PC port in September of this year, we were very surprised at the quality of the DX12 implementation, which kind of forms the backbone, obviously, for the ray tracing implementation in this game. So my question there to Nixxes would be, how did you manage to have such an impressive DX12 implementation in this game versus what we usually see? We're not used to seeing NVIDIA and AMD hardware performing both so much better in DX12.
I feel part of it is that we started on DX12 quite a long time ago. We already, when it only had just been out for Rise of the Tomb Raider, we really tried to push on DX12 and get it into our game. That was, I would say, less successful. I think for a lot of consumers it was still beneficial, but certainly not for all of them. And since then, we really kept pushing on that, optimizing that further, looking at what really the bottlenecks were, why it wasn't performing well on certain hardware. One big thing we spent a lot of time on, also Michiel actually spent a lot of time having better support for swapping resources between video and system memory. DX12 gives us a lot more support for that, so we can make much smarter decisions. And a lot of those helped to just continued efforts and optimization helped to make sure that when we got to Shadow of the Tomb Raider, bring all that work in and really have good performance. And I think to us it's not entirely unexpected. We've been on the Nixxes side been concerned about a lot of the API overhead from DX11 for a long time, and been seeing it as a bottleneck. And so it's really been a push on our side as well, even before that with other APIs to have lower overhead APIs. And we just slowly are getting to the point where that became more and more relevant, is more and more relevant for users. As games try to push the hardware further, the bottlenecks become more apparent, and that way the gain of DX12 also becomes more apparent, coupled with just all that experience we built, starting with Rise of the Tomb Raider quite a while ago to get it in.
And would Michael also like to contribute at all to that question? Basically about the DX12 implementation, how did you got it up to the standard it is at, where we see both, I say, improvements on the CPU side of things and on the GPU side, which we don't always expect always.
Can you hear me now or not?
We can hear you perfectly.
Oh, okay, that's great. Okay, well, we started off the PC port of Shadow of the Tomb Raider I think it was maybe 2 years before ship, and we mainly focused on improving the DX12 implementation. So it was a small team, but it was a team that could do optimizations.
Michael says, we mostly ported the async compute work from the console side, but we did it selectively since the overhead is much larger than on the consoles. We didn't end up using that much asynchronous compute in the original version, actually. I think the hair simulation and some lighting. But it seemed like it had a very large win when looking over at how it applies to ray tracing, which is something I think I'm going to ask a question about right now. Basically, when we played the game at Gamescom of this year, we obviously played an out-of-date build, with very nascent implementation, I'm assuming, of ray tracing at that point in time for the shadows. I would actually ask the question, what changed in terms of major things between the Gamescom build I would have played in around August and the most recent patch, which was just shipped, because the performance is quite different. Back then, I think it was 1080p if I looked properly, and running on an RTX 2080 Ti, and was definitely below 60 FPS quite often. But now, even with the ultra settings, just going through the benchmark, you can see it doesn't actually drop below 60 with ray tracing set to ultra at 1080p. So what were some of the major optimizations and kind of implementation changes?
There were other changes as well, right? I mean, we drastically sped up denoising and ray tracing by using effectively to band the parts of the screen that we use for local lights. So think about a candle on a table. It obviously doesn't have a large sphere of influence. You can effectively mask that area off and make sure that you only shoot rays in the local area, and the same for the denoising of that.
The variable ray count, I think, was something that came in later potentially. We were just doing a bunch more rays, I suspect.
That could be true as well, actually. Yeah.
Yeah, I think for the Gamescom demo we had probably 3 rays per pixel, pretty much everywhere, something like
wow.
that.
Yeah, it says in the chat, between Gamescom and now, we almost changed everything. We did a lot of optimizations, the API was finalized, and the drivers were a lot better. Back then, we were working on pre-release hardware, drivers, operating system API, etc. And the implementation we did was pretty naive.
And then certainly we spoke about async compute a bit, but doing all the, I think initially one big challenge really was getting the BVHs updated as the changes. And there's quite some moving stuff and some destructibles in that level. And moving a lot of that to async compute and further driver optimizations to that process of updating the BVH, that really helps because it moved it all to a parallel process, and which didn't really impact the frame rate significantly.
Yeah, I think we also did a lot of work, or actually Michiel did all that work, but the work was done to make sure that not always the highest LODs go into the acceleration structure, but that the right LOD goes into the acceleration structure, and also that only objects go into the acceleration structure that can actually be, or would be drawn into, can be seen by a light, essentially. So that you don't necessarily throw everything into it, but only the stuff you really need.
And another major thing that was done was we restricted which geometry was added to the BVH by distance from the camera. You can think of this as akin to cascades, shadow cascades, where you have 4 cascades in the game. The closest 2 are added to the BVH, but the furthest 2 are not, and those are just shadow mapped instead, which I don't believe was done for Gamescom. I think it was done after.
No, in Gamescom we just had everything on and everything on optimal. That's pretty much what the short answer would be. I think one thing that's important to realize there, like as I think you know, when we were at Gamescom, and especially just before Gamescom, while we had been working on some emulation layers to really test this and some other hardware that wasn't final hardware, not even close to final hardware, we didn't really have much of an idea at all how fast it was going to run. So we weren't really that focused on optimizing it yet. We didn't really know what to optimize to. What would the target be? How fast would it go at all? We obviously had some of that hardware before Gamescom, but there wasn't a lot of time at that point to really put all that in motion. So really all of that reaction to actual performance and optimizing it all happened after Gamescom.
Yeah, most of it. And there were also really like tons of drive optimizations happened between Gamescom and the release. Lots of stuff related to acceleration structure building, updating, and so on. And same thing for shader compilation. So the driver improved a lot.
I guess since you guys talked about it a couple times now, you guys are still utilizing shadow maps to a certain degree, and that is very evident when you go between the various settings, between off, obviously, medium, high, and ultra. It would be great to hear specifically in terms of either ray per pixel, the resolution of the denoising, or which lights actually get RT shadows and their fidelity. What are the differences between the various quality presets that we're offered right now?
I'm going to try to field that, and Michiel might want to correct me over chat if I get anything wrong. But if we start at the lowest end, our medium setting, really that's about, we really just do some local lights, and they're selected by artists which local lights get the most value from that get RT shadows. Everything else stays shadow mapped. To me, that's even in some way the biggest gain, because those local, it's local point lights, and those point lights are really hard, or at least really expensive to do with shadow maps. So it's often things that wouldn't get a shadow at all beforehand, and then would get a nice shadow with ray tracing, because that's just so much cheaper with ray tracing. So at medium, we just turn those on, and I think that gets you a big bang for the buck, because you really go from nothing to having a great shadow on those things. But everything else, like the sunlight, for example, and many other lights, we just leave shadow mapped as normal. And we really have great shadow map code from the PC version without RTX, so we get good visuals on that either way. Then at high, we do actually we move a lot more lights, like all the sunlights go into RTX, so the size of the sun, distance of sun, all of that plays into softness of shadows, much better contact hardening. But the performance impact, because everything does a lot of things go through the RTX pipeline, starts impacting. We do still, as John said, do shadow maps all the way in the distance. And another reason we use shadow maps still is for translucent objects, for translucent objects to receive a shadow. But otherwise, there's certainly a lot more ray tracing going on in the medium. Then ultra keeps most of the same things in terms of what lights are getting shadow, but all those shadows, we also add translucency to objects that the light goes through. So if we for example have some translucent canopy or something, then that shadow you wouldn't have a fully occluded shadow. Some of the light would seep through, some of the light would not, and depending on how many things are occluding something, more light makes it through for a more realistic shadow. John, I think there's also some changes related to the denoiser and the other shadow rays on Ultra. Is that right? Can you clarify that?
Oh yes, that's right. Yeah, on the Ultra setting we have what we call adaptive filters, where we do one ray per pixel, and then we take a look at the result of that and filter basically examine a small neighborhood and decide whether we want to shoot an additional 1 or 2 rays per pixel. And it does that based on looking at the frequency of the hit distance to see whether there's much variation in there. If there's a high frequency of variation, then it's going to shoot. a few more rays per pixel. And in that way, it gives you slightly higher quality contact shadows. But it's obviously more expensive, which is why it's in the ultra setting.
And I think denoising-wise, John, I think we stuck to half res in the end, right?
That was quite expensive to go full res, and we didn't really get any significant visual gains out of it. They can be found if you look, but the performance cost was pretty significant.
So looking actually at an average scene, let's just say, with, I would say, like the sun and maybe 2 other lights with RT shadows, what is the most expensive part of that frame usually? When doing ray trace shadows? Is it creating the acceleration structure? Is it the amount of rays cast? Or is it have to do with how much intervening geometry there is? Or the denoiser, which is half res, obviously, at this point?
It's a complicated, it really depends on the scene. So I would say if you're outdoor with the sun, and so, I mean, with the local light source, it always depends, as John has said, how big are they on screen? Because only pixels that are really touched by the light source, so basically that intersect the volume of the light source, those guys would, only for these pixels would you even send rays, and then we would only denoise sort of a local rectangle around these lights. So they are cheap if they're not big on screen. If of course you have a bunch of lights that are all pretty big on screen, then the cost sums up because you literally send 1 ray per pixel for full screen for all of the lights. So it really depends. Yeah, that's really it, right? And outdoors it depends on how much. What we found is that alpha testing is expensive. So in the jungle scenes, the rays are expensive because there's so much layers of alpha testing going on, specifically in ultra.
Mika says in the chat, translucent geometry is even more expensive since we can visit multiple geometry for one ray.
Yeah, and I think overall it's fair to say, like, I fully agree with it's a complicated question, but in the typical scenario you described, where there's sort of 2 local lights in the sun tends to be the largest performance impact because it covers the whole screen. Not literally, but the largest part. And those rays, they have a really long way to travel. They traverse everything, right? They go from the ground, for example, all the way up to the sun. And sure, near the end of that, there's not much going on, but you do traverse through a large part of it, while a smaller candle, for example, the rays that we cast there are much shorter, so those ray costs are cheaper as well.
As the other folks have said, it is scene dependent. We tested spots in the game, and we found that, I think, as you are with the forest scenes were the most expensive. We found that the actual trace cost was the dominating factor there, and it was because of this having to trace through primitives for alpha-tested textures. And that's probably the biggest pain point, unless anyone disagrees.
No, absolutely. I mean, the other thing is obviously with the sun, as Jürgen said, is very expensive because also tracing the sun means you have quite a lot of objects in the acceleration structure because the sun can see a lot of the scene, right? So that's the way it is. And the thing is, updating the acceleration structure itself, I mean, that again is very scene dependent. Most of the time, we can actually totally hide the cost through async compute, as Michiel said. So you sort of get it for free, but then for some expensive scenes, that's not the case. But for many scenes, it is. It's literally free.
Mika says in the chat, the acceleration structure building is currently almost free because it's overlapped with the depth and shadow map passes.
Yeah, in a way, it's jungle was bad itself because in jungle we try to have a lot of moving foliage, so then there's a lot of dynamic things going on in the acceleration structure, and that doesn't make it any better. But still, we can hide most of it. I think in the more, well, I don't know what you would consider typical, but in a more typical scene where there's less moving stuff, there's just sort of some animated characters, maybe some flags, but a lot of the scene overall is static, and the BVH cost is really pretty slim, and I think, and often completely hidden. And to me, that is actually quite powerful about this. Like, shadow map cost would never be hidden that well, and if the BVH is fully hidden, then it's kind of nice. You can just trace into it later, and you don't have this large cost for rendering those shadow maps because that BVH is just updated in the background.
So for specialty cases, you were mentioning how for transparency to to receive shadows, and I would imagine also maybe Laura's hair receiving shadows, and a couple other cases, you still keep shadow maps around. Also probably, I would imagine, for the volumetric lighting, so that it knows where it should cut off and have shadows within the volume itself. How did you work around getting to learn where you still needed to keep shadow maps, basically? And do you see a future where that will not be the case anymore through a different use of ray trace shadows or a more complete usage of them?
I think we're partially already getting there. Like for a lot of those extra point lights we have, we only do the ray tracing. We don't do the shadow maps. So I think that's a big step forward. Within the current technology, I think it's going to be pretty hard for receive translucencies that receive light to get rid of it. So you could do some complex depth peeling things, but the cost there would be pretty significant as well. There are things that are sort of being discussed for the future to expand ray tracing and how you can ray trace that might make that better. So but it's certainly something I'm really enthusiastic about. I think if shadow maps, if you can get rid of the shadow map and you only need to have BVH, then I think things are really trending almost in the positive direction performance-wise.
Yeah, I mean, absolutely. Also, I think the thing to realize is that if you want to do translucent or shadow translucent geometry like particles or Laura's hair, as you say, Alex, with ray tracing you need to shoot rays from the pixel shader, or as Julian explained, like do a very complicated depth peeling scheme of some kind. And there are indeed cases where ray trace is a lot faster. I think there was a presentation of Unreal Engine 4 where they showed an outdoor scene with lots of, in this case the famous teapot, but lots of them. And in this case, the shadow map shadows were actually quite a bit slower than the ray trace shadows. So there are definitely cases where this is happening already.
I guess a question after that would be visual positives from ray tracing that you particularly are proud of or particularly liked as a result that were more elegant. Just playing the game myself, one of the things that I noticed was usually contact shadows and extra shadows. So I guess the phrase is concave surface of something where the inside lip of like a wheel well would have the shadow kind of adjacent to it, not actually connecting correctly, or small detail on like Laura's body or her face actually having a much more, I guess, contiguous shadow detail where it didn't look like the shadows were floating to the side. So what visual advantages were you kind of most proud of that you get over shadow maps with your implementation?
Contact shadows that you're talking about, the phenomenon where it's not attached, is called Peter panning, and there are two major shadow map artifacts. One is Peter panning, where you're adding a bias to the depth value in the depth map before you do the shadow computation, and that bias will never be correct in all cases, and so you get that disconnect. Ray tracing makes that essentially disappear, and so that is a major artifact that exists across all shadow map implementations forever. And that and shadow acne, which is also caused by this bias, are substantially reduced when you ray trace the shadows. And for me, I look very closely at shadows in games, and to see this not exist anymore makes me really excited, because it's something that you can really only do with ray tracing.
I think some of that extra detail, that's certainly one really interesting aspect, and it's why for example, when we ray trace a light, we turn off the screen space contact shadows for that light, because we no longer need to do screen space contact shadows. The ray tracer gets enough detail to show all that as well. But I think it gets more exciting if we look at some cases where we have real area lights or other light sources that in essence are really soft. For example, when we have a fire giving off a light, that's not a bright point light with a really sharp shadow. No, we can have really large area lights there effectively, like this fire is giving off light. And I feel that creates a lot more natural look there, and something where a normal shadow map wouldn't have really produced something realistic.
So just to add something here that Mikhail put in the chat window, he said, I personally love the translucent shadows. That's really not possible with shadow mapping.
One thing that I noticed that I found going back to that Peter panning issue and the acne problem was when even though the base shadow maps, I would say, in Shadow of the Tomb Raider are actually pretty great. I actually really like the way they're filtered, particularly. But when you advance forward, you can see the shadow maps cascades kind of changing as you get closer. And obviously those distant shadow maps are still used in the ray tracing implementation, but for those closest ones, you don't ever see that kind of moving line with the screen as you advance forward, as shadows kind of flip to higher res versions of themselves. And that looked particularly great, actually. And it's no longer a distraction. It's a different form of like aliasing, because you see rapid change of movement on the screen. And I found that very great looking. To get back to the question of how aerial light shadows are done, actually. So what type of aerial lights are supported, and is it an arbitrary shape, or is it like a disc or a planar kind of rectangular shape? And how does basically aerial light shadows work?
Yeah, I mean, let me just say, this is all the work we've done was in the end pioneered by John and other people inside NVIDIA. So in the end, we've sort of adapted this to Shadow of the Tomb Raider. But the way it works is essentially, for the point lights it's very simple. It's not really a point, but it's essentially a sphere. So it is all the lights we have are area lights, right? So the point lights are actually sphere lights, so they can have, and as you said, soft shadows at least far away from the blocker. You get when the radius of the sphere or point light is big. We do cone lights, and for the cone lights, you can imagine this like let's say a desk lamp, right, that casts a cone of light, and inside this desk lamp you could imagine sort of a light bulb, right? So you sort of see half of a light bulb sticking out of the desk lamp, and that bulb has dimensions. It has an extent, and that's the area we use for the cone lights. Right? And then we also do rectangular cone lights, and for these guys you can sort of imagine it is a rectangle that is casting a cone, right? And and the rectangle can have any dimensions essentially, and we basically we shoot enough rays to make sure we cover enough or find out how much of that rectangle can be seen over the neighborhood of pixels to see how soft the shadow would be at a certain point. For the sunlight, it's slightly different because the sun only has even I think physically the sun has a angular extent. So it's basically like if you look at the sphere around you, then the sun has a certain angular radius that is defined in terms of how radiance it takes in this on this virtual sphere around you, and this is how we do it as well. So basically the sun has an angular extent that can be set by the artist, and that defines how smooth the shadows get if the blocker and the receiver of the shadow are far apart.
So it was mentioned both in the presentation and by yourselves as well that there is an artist decision here. It's not just blindly applying ray tracing to every light and every shadow. So how is that process basically done? Is it per scene? And how would you like to see that be done in the future for future titles where this is more natively implemented? And basically kind of is that the most efficient way you would see it be done in the future, or would you prefer it to be more systematic?
I think partially it has to be somewhat of an artistic decision. When we are talking about things like light size, that is a physical property in the world, but if they just altered plain spotlights, for example, that have no size and no parameters were set, then there's nothing you can do there. They really will have to go in as they alter their lights. So in this case, we did it afterwards, but you can do it as you're building the content immediately to properly indicate what the size of that light is. The same with those area lights. Before, they might have put in a couple of different lights to fake the effect of the area lights. From that, we couldn't automatically go make an area light. We would require an artist to actually alter an area light, put that in properly, and get that result. And it also, certainly in this case, allows the artist to make good performance trade-off decisions. If they really don't get much gain out of it, they can leave them non-ray traced. And for other lights where they do get a lot of gain, those would be the best ones to turn on ray tracing. So it really is just more parameters, I guess, on lights, and that's because they're actually, I mean, those physically, there are different physical parameters that we didn't use to set that we now do need to set. I mean, you can just mix them up, but I don't think, as we're trying to be more realistic, I don't think that's the answer. We actually have to alter the things that need to be altered, I guess, that are an artistic decision.
In terms of, just this is a slight aside question, but I noticed that the transparency shadows still are obviously of like a gray, dark nature. Was there ever a discussion about doing colored transparency shadows at some point?
I think the literal answer to that is no. I don't recall a discussion on that.
No, we
That means somebody else would never.
Mikael says in the chat here, I think we brought it up, yeah, actually, but with stained glass windows. It's not as trivial as you might think. And he has a little smiley face there.
It's true, but in theory, we could have picked up some color from the geometry we pass through as we do the alpha test anyway. I guess we could have done it, but I think we were busy enough.
And I think also it would have required us to change the render target formats for relation shadows and so on. It looks ruled out to being definitely one for the future. We have been thinking about it internally at Nvidia, but yeah, this is iteration 1.
So to get to the denoising step, it's a spatial denoiser from what I could read from the GTC presentation, which is different than we've seen in other titles before. So when shadows move in this game, they don't actually seem to leave a trail of pixels behind them at all, which is something we've come to expect slightly from ray tracing, basically a temporal component. What was the decision process behind the denoising step, and how does it function on a simplistic level, obviously, I would say?
So I think I can answer that one. So the decision was taken like a year and a half ago to attempt to do spatial-only denoising for shadows and a bunch of other techniques, partly because of the problem that you highlighted with temporal denoising, where you can see that there's some lag where it's effectively catching up with dynamic objects moving on the screen and so on. And in order to make that possible, we spent about a year working on it, so it was quite in-depth. But to cut a long story short there, instead of just doing horizontal and vertical filtering, which is the normal way you do separable filtering, we actually looked at the light direction as projected down onto the receiving plane for a screen pixel, and then we effectively make the filter directions aligned to that. So that's what we call anisotropic filtering rather than isotropic filtering. And it makes a huge difference to the quality that you're able to achieve. And I guess the other major thing there that was done to get really high quality was to use the world space positions of the samples that we're reading in the filter as weights. So we would calculate what the projected size of the light would be in world space, and then we would take the center of the filter in world space. And for each sample that we read, we look at the world space distance to the center and decide based on that compared to the light size what the filter weight should be. And this drastically increases the quality of the filtering. It was quite expensive, and so we then went about doing a lot of work to make that go fast. So just some of the things that we did was obviously putting viewports around things and making sure we don't do unnecessary work. One of the other main things we did was we created a penumbra mask. So this is all the pixels which aren't fully white or fully black in the shadow buffer. They're all the pixels that basically need filtering, nothing else does. And in many typical scenes, you can mask out an awful lot of the screen as not needing denoising. So it's things like that we did to make it go as fast as it does. The other thing, of course, was doing it at half resolution. And we spent a long time getting that right. In order to get that right, we needed to be able to detect all the edge pixels of objects in the scene and mark those as sort of complicated pixels. All the simple pixels we would do at half resolution, all the complex edge pixels we did denoise at full resolution. And this allows you to sort of preserve all the accurate high resolution edges, but do all the simpler case stuff really fast at low resolution.
Yeah, John, I think the other thing you really solved nicely in this denoiser is the overlapping penumbra stuff, right? It's, I guess,
Absolutely. I mean, this is one thing. So if you imagine, say, Lara walking underneath a tall tree, and the leaves cast very soft shadows onto the ground from the tree, and obviously Lara's shadow, she's close to the ground, is. And what you tend to find with shadow mapping techniques such as DXR, DHS, you get filter interference from the far away object, far away occluders, and the close by occluders. They tend to sort of get averaged together, and then you get this sort of blurry mess instead of what you really want to see. And we kind of solved this problem because it's still an issue for a screen space denoiser, which is what this is. But essentially what we did was we looked at the size of a pixel in screen space, and we had a look at the hit distance for the center pixel traversed. As we traversed the filter, we would estimate what we think the hit distance should be, and we would compare that to the actual sampled hit distance. So taking the ratio of those two things, you can multiply it by the filter weight. And so if they're close to being the same value, you get a good contribution from that sample. And if they're very different, you get a low contribution. And it does a very good job of making sure that you preserve the shadow detail as you would expect. But again, that took quite a while for us to get right.
Okay. I think that's a lot of really good information about the ray tracing itself, very specifically. But as part of this, RTX update to the game, essentially, there was also the introduction of deep learning surplus sampling, DLSS. And for us on the channel, we are actually a pretty big fan of both temporal anti-aliasing in general and reconstruction techniques. Basically, any way to get as more performance as possible while also maintaining image quality. We're actually really big fans of that at Digital Foundry. So a very basic question for those who are involved at all with DLSS integration in this title would be what, for at least 4K output, and I guess 1440p output, or 1080p output, what is the original internal resolution that the game is running at before DLSS kicks in?
It actually depends on the what the driver says.
Oh, okay, that's very interesting.
So basically, the game queries the DLSS runtime and says this resolution I want to render, and then the runtime tells it that is the scaling factor that you need to divide by or multiply by if the scaling factor is lower than 1 that you want to render at, and that's how it works. But it's roughly, I don't know, it's like 0. I think it's, I don't want to call the exact numbers because I don't even know them by heart, but it is.
I think if you don't know them, we can't call them out, Holger. And
we can't. No, it is exactly.
You can get that information too if you want, but it's also dependent on the GPU as well, isn't it?
It is, and it also it is basically the target is changing. Right? People are still improving DLSS. The quality, so it is entirely possible that new drivers might change things. So, but the good thing is that the game basically can query what the driver or what the runtime wants it to do, what it thinks will yield the best quality, and we can basically update that even if the game has already shipped.
So looking at the quality of the pixels itself that are generated, like I was just testing the game out at an RTX 2080 Ti, and I was playing it at 4K and 1440p. And one thing I've noticed a lot in DLSS titles is both the kind of styled look I would call to these kind of pixels in the end, and also the kind of the way transparency is affected by it. I mean, I don't obviously know how much you can talk about it, but specifically, how are transparent screen elements handled by DLSS currently, and how much effect does the, I guess, information fed into it, the super high resolution images, affect the styling and quality of the pixels in the end?
Yeah, I think some of these questions we probably need to delegate because I can't really answer the question about the transparency, because that's something we need to pass on to the deep learning experts. I think the one thing we can say is that there was a presentation at GDC, and I think it should be available very, very soon. And I mean, we can definitely walk you through sort of the steps, what happens, right? You know that, or what is definitely publicly known and has been discussed is that it is basically a two-step process. There's one process that takes the original or the rendered resolution and basically refines that image by reconstructing details that the network has learned. So basically it improves the quality of the image. And then in a second step, that image is scaled up later on by a different neural network. So just for your understanding of the whole process, basically sort of these are the two steps that happen.
I think one thing that we might be able to say is that transparent or translucent objects may not actually have velocity vectors.
Right. Yes.
And that may be why we see some differences in quality in those regions. Is this kind of like the direction that the question was going in?
Yeah, basically. Also, just kind of to pick your brain on basically how DLSS integration works, because we can only see from the outside looking at the pixels always.
As John says, I mean, there are two things that go into the DLSS library at the moment in the current integration. It is obviously the color image itself, and then the motion vectors. So the motion vectors are also needed by temporally A and obviously motion blur and stuff like this, but the image it basically refines or improves the image quality before the upscaling. That network actually takes in the motion vectors as well.
And in terms of like the training, we capture lots of images from the game which are rendered at higher resolution than you would see on the screen. I think it's 3 times the resolution, and those are used as reference images for the training process.
No, hang on, it's even 64 samples actually. It's 8x8. So we definitely produce a lot of high quality images to train in network on.
Just a slight aside question, but when generating those ultra, 8x8 super sampled images from dealing with taking ultra high resolution screenshots, we can see that screen space effects can scale differently across high resolutions. Did you have to take that at all into account? Like the size of bloom, the way that looks, for example?
Well, the way it's done is basically that you're capturing, ultimately rendering to produce a lower res image, so you can adjust some of the texture details accordingly in the hardware. So I can't really say more. Some of this is really quite detailed and quite complicated, but in the end you adapt for that. You know that, otherwise the thing you say would happen, right? So we sort of predict that and say, yeah, okay, we need to adjust some of that.
Another thing I noticed when running the game with DLSS on, with using ray tracing versus not using ray tracing, was that at certain screen angles, it looked like, this is maybe a question also that would apply to John, actually. It looked like the denoising was working differently with DLSS on versus with it off, and versus shadow maps, because of obviously the differing internal resolution of that image. Is there any reason why you would think something like that would occur, perchance? Like why the edges of shadows would look a little different with DLSS on versus with them off?
Well, there's certainly no change in behavior to the way the ray tracing itself is done or how the denoising is done. So the differences would be coming from DLAA and the upscaling. I'm not sure why you would. I'm probably not the expert on answering why that would be the case. I'm not sure. I think
what it would come down to is that, I mean, we were like, I think John, anyway, John does have the expertise, like what he's saying, that we're not actually doing something different. It's actually the same ray tracing, the same denoiser, and then ultimately, yes, you do see some, I totally believe you if you say that you see some differences, but that would really have to go to a DLSS expert. But it really wouldn't be all that different from, hey, it's just an image that shows that, and why does DLSS pick up on that in a certain way? So I think it sounds like we don't have a DLSS expert on the call to explain that.
Yeah, so we have here, Mikhail just put, with DLSS and TAA, we do a jitter, and that might cause a difference in noise.
That's great. And I guess the last question I would have regarding DLSS would be, just looking at Anthem and Metro Exodus recently, I noticed a greater level of image stability. So an edge may not flicker as much with DLSS on versus TAA in those games. And I also noticed something very similar in Shadow of the Tomb Raider here. Is there any specific reason why DLSS would offer a more stable image, even though we always think of TAA offering extremely stable images?
You have the image that has no anti-aliasing applied to it, but the network sort of knows how to. Let's say you have a line. Let's say you have we don't have this in the game, but let's say you have a telephone line somewhere like that hangs in there, and sometimes you may see some pixels missing in this thin line, right? But then the basically the improvement part of the network would know how to reconstruct these pixels, right? This is so the information. It basically learns this information or has information that allows it to reconstruct features that you wouldn't really see anymore. And that's obviously something that TAA would be hard-pressed to do, right? So this is where the deep learning approach to improve the image is clearly superior.
I guess I'll try one last question because you never know. Basically, the DLS image that is shot out there and is used in the game, is there also some sort of post-processing step on top of that as well, regarding sharpening and or anything like that, kind of color correction, making sure it works for HDR?
No, there's nothing. It's really just there's the two-step, there's the two networks that run over the image, but other than that, nothing else happens. That's
great. So I guess a last question I would ask before I let you all go, and I thank you, of course, for doing this, would be if there was something that you're very proud of or something that you're excited about for the future for ray tracing and its specific implementation here or just in general, it would be great to hear from you guys, because this is a question I asked both the Metro and 4A guys and also the Frostbite guys, and they had a lot to say there. So what are some things that excite you or that you were very proud of here from your work?
I could kick off on that one. I started working on ray tracing before we had the ray tracing hardware, and I have to say I really didn't think we'd get to the place where we were looking at having 16 lights, which is the maximum in Tomb Raider, being ray traced and denoised. I just didn't think that we'd get it that performance. So from that point of view, I was blown away by where we got to. Let someone else chime in.
Yeah, absolutely. I mean, I think in general, right? I mean, okay, you've probably heard this before, but ray tracing it solves problems you just couldn't solve before easily, right? Because rasterization is fundamentally only good at providing visibility from one point of view, right? So of course you could then render multiple images, but this gets really, really expensive. But if you want to know from any point in the scene, and you want to, let's say, look along some arbitrary direction, I think that the only way to really solve this is a form of ray tracing, right? And this means we now can solve problems that you could otherwise only approximate and or provide with like static pre-computed solutions. So we can now do these things realistically and dynamically, and this is why ray tracing is so cool, because you have a new tool in the box that solves these fundamental problems we couldn't solve before.
I think from my side, I think it's also just been a learning experience, and so taking this from what we did on Shadow of the Tomb Raider to a new title, I think we have so much of a better idea where we would want to apply ray tracing, what things we would want to use it for. I think we would have a better insight into what content altering is needed for it. That really only started happening as we got our implementation going and we slowly got some people on. So the more we can alter it in at the start, the better results I feel we can get. I think we can go much further with smaller point lights and smaller point lights having shadows. And that way, like getting like even the 16 light number that John mentioned, we can go much further than that for many, many smaller lights. Which in a game like Tomb Raider, we tend to have a lot of small, tiny light sources, and just the fact that all those could become shadow casting, I think that's really exciting. And then there's all these other things we could apply ray tracing to. That I think as we get better about using it efficiently, we free up some GPU power to use for some other things. And yeah, so we really only touched on shadows, and there's so many other use cases out there that as we move to newer games, I think there's great things we can do.
I think one thing I can say this while some heels typing is that I think we're all pretty proud about the fact. I mean, this is the first game ever to ship with ray traced area light shadows, with soft shadows. And I think, I mean, this is the thing we're most proud of, right? To ship the first game that has these ray traced shadows, and we're particularly proud, I think, of the area light shadows, like the rectangular light shadows, like in the Day of the Dead scene, where you can see like these neon signs that cast really soft shadows. This is really the stuff we're I think, at least I'm most proud of.
Yeah, that kind of connects back to altering on my side, right? The more we can think about it from the start and leverage those things, I think we can really make something that shines beyond what we've done right now. So that's what I'm really excited for the future. I think we have good examples of this here, but now that we know we can do that, we can really go further with that in a new game.
And just to piggyback off of Holger, not only is it the first with ray traced area light shadows, but it's the first, I believe, with transparency in the shadows as well. And now that we have, as Holger said, a new tool in our box, we have coherent visibility with rasterization and incoherent visibility testing with ray tracing. And these are the two fundamental tools you need to efficiently solve problems in light transport. So you can do things like recursive light transport simulation and transparent light simulation that was simply just not possible before.
And just to add here the response from Mikhail as well, I was very happy that we got it to perform very well, especially compared to the Gamescom demo. I'm also proud of the AFR implementation that we have.
Yeah, this is something we actually have not tested too much at Digital Foundry. We kind of moved a bit away from testing multi-GPU over time for a lot of reasons. But now that you say that, I definitely think we're going to put this game up to the test, see how far we can push it. As someone who used SLI back in the 8800 and 470, GTX 470 days, I moved back to single GPU now. But I'm grateful that you all came here to this call, and it's definitely going to be a really great video. I think usually we've done these interviews separately, and they don't get as much traction. But I think in the form of a video, hearing directly from you all who worked on this, it's going to come across really great.
Thanks a lot for your time today, Alex, on this, and everyone else on the call.
Thanks, Alex.
It's really useful.
So you somehow got to the end of this video, in which case please do like and subscribe and hit that little bell in the corner to be informed as soon as Digital Foundry posts a video. And you can also ensure that more interviews like this can happen in the future. Also, be sure to tell me how you felt about this format of an interview in a comment below, and what you would perhaps like to change about it, or ping me and Digital Foundry on Twitter. And as always, this is Alex, bidding you farewell und auf Wiedersehen.